Have you ever wondered how it all ends? Not just your life, or humanity, or even Earth, but everything. Every star, every galaxy, every atom in existence. We spend so much time thinking about beginnings, about the Big Bang, about the moment when space and time exploded into being. But what about the end? What happens when the last star burns out? When the final black hole evaporates? When the universe grows so cold and dark that nothing, absolutely nothing can happen anymore? Tonight, we drift toward that ending, not with fear, but with quiet acceptance, to witness the longest goodbye the cosmos will ever know. This is not a story of destruction. It's a story of fading, of entropy, of the slow, inevitable unwinding of everything that exists. So close your eyes, let the weight of eternity settle gently around you, and follow me into the final, endless night. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1, the next trillion years. The stelliferous era ends. Right now, as you read these words, the universe is in its prime. Stars are forming, galaxies are colliding, planets are being born from disks of dust and gas. According to NASA's Goddard Space Flight Center, about 7 new stars ignite every year in the Milky Way alone. Multiply that across the estimated 2 trillion galaxies in the observable universe, and you get an incomprehensible number. The cosmos is alive, burning, shining with the light of countless nuclear furnaces. But this era, this age of starlight, is temporary. Astronomers call it the stelliferous era, from the Latin words meaning star-bearing. It's the period when stars dominate the universe, when fusion reactions power the cosmos, when light pushes back the darkness. We're living in it now, and we have been since the first stars ignited about 100 million years after the Big Bang. But it won't last forever. Stars form from clouds of hydrogen and helium, the primordial elements forged in the Big Bang. Gravity pulls these clouds together, compressing them until the pressure and temperature at their cores become high enough to ignite fusion. Hydrogen atoms smash together, forming helium and releasing enormous amounts of energy in the process. This energy, in the form of light and heat, is what makes stars shine. It's what allows planets to exist, atmospheres to form, and life to emerge. But there's a problem. According to ESA's Planck satellite and NASA's WMAP mission, hydrogen makes up about 75% of the universe's normal matter, but it's being consumed. Every star that burns is converting hydrogen into helium and eventually into heavier elements like carbon, oxygen, and iron. These heavier elements can't fuel stars efficiently. Once a star exhausts its hydrogen, it begins to die. Small stars like red dwarfs can burn for trillions of years, but eventually, even they run out of fuel. The universe's supply of star-forming material is finite. Over time, the great clouds of gas that give birth to stars are being depleted. Some of their matter gets locked away in stars. Some gets ejected into intergalactic space by supernova explosions. Some falls into black holes. According to simulations by NASA's Jet Propulsion Laboratory, star formation has been declining for the past 10 billion years. We're already past the peak. The universe will never make stars as quickly as it once did. In about 1 trillion years, give or take a few hundred billion, the last conventional star will ignite. After that, no new stars will form. The universe will still contain stars at that point, many of them red dwarfs that will continue burning for another 10 trillion years or more. But the era of star formation will be over. The stelliferous era will end, and the universe will enter a new phase, one defined not by creation, but by the slow dimming of existing light. The James Webb Space Telescope has captured images of galaxies as they appeared billions of years ago, when star formation was at its peak. These ancient galaxies glow with the light of millions of young hot stars, their ultraviolet radiation ionizing the surrounding gas. But look at modern galaxies, and you see something different. Star formation is slower, more sporadic. Large elliptical galaxies, formed from mergers, contain mostly old stars, their light dim and red. They're previews of what all galaxies will become, fossil structures filled with dying embers. As star formation declines, the universe will grow darker. The brilliant blue stars, the supergiants that outshine entire galaxies, will be the first to go. They burn hot and fast, exhausting their fuel in just a few million years. Next will be the medium-sized stars like our Sun, which last about 10 billion years. In 5 billion years, according to NASA's Solar Dynamics Observatory, our Sun will exhaust its hydrogen, expand into a red giant, and eventually shed its outer layers, leaving behind a cooling white dwarf. By the time we reach the end of the stelliferous era, around 100 trillion years from now, the only stars still burning will be red dwarfs, small cool stars that sip their fuel slowly. ESA's Gaia mission has cataloged billions of stars in the Milky Way, revealing that red dwarfs make up about 70% of all stars. They're the most common type, and they'll be the last lights in the universe. Some red dwarfs will shine for 10 trillion years. A few might last even longer, up to 20 trillion years or more. But even red dwarfs eventually die. When they exhaust their hydrogen, they don't explode like larger stars. They simply cool, fading from red to orange to yellow to white, eventually becoming black dwarfs, cold, dark remnants no longer capable of fusion. These objects will drift through space, invisible, radiating only the faint heat left over from their stellar lives. As physicist Freeman Dyson once wrote, "The universe is not running down to a state of heat death. It is running down to a state of cold death." By the end of the stelliferous era, the universe will be filled not with light, but with cooling embers, the corpses of stars scattered across expanding space. Take a slow breath. Right now, you're living in the universe's golden age, the brief period when stars are common, when galaxies glow with light, when the cosmos is warm and bright. But this age is just a moment in cosmic time. It's already ending. The peak of star formation passed billions of years ago, and we're on the downward slope, drifting toward a future where darkness is the default and light is just a fading memory. And as we watch the last stars flicker out, a new question emerges. What happens after the stelliferous era ends? What comes next in the timeline of cosmic death? That's where we drift now. Part 2. The degenerate era. When dead stars outnumber the living, when the last red dwarf finally exhausts its fuel, sometime around 100 trillion years from now, the universe will enter what astronomers call the degenerate era. This is the age of dead stars, when the cosmos is dominated not by fusion-powered suns, but by their cooling remnants, white dwarfs, neutron stars, and black dwarfs. It's called the degenerate era because these objects are made of degenerate matter, material compressed to such extreme densities that quantum mechanical effects prevent it from collapsing further. According to NASA's Chandra X-ray Observatory, white dwarfs are the fate of about 97% of all stars. When a star like our Sun exhausts its hydrogen, it swells into a red giant, then sheds its outer layers, leaving behind a hot, dense core about the size of Earth, but containing roughly half the Sun's mass. This core is a white dwarf, no longer undergoing fusion, but still radiating heat left over from its active life. White dwarfs are incredibly hot when they first form, with surface temperatures exceeding 100,000 degrees Celsius. But they're also incredibly small, which means they radiate their heat slowly. According to calculations by NASA's Goddard Space Flight Center, A white dwarf cools at a predictable rate, fading over billions of years. After about 10 billion years, it cools enough to become invisible to optical telescopes. After 100 trillion years, it becomes a black dwarf, an object so cold it no longer emits any light at all. Black dwarfs are theoretical. The universe isn't old enough for any white dwarfs to have cooled into black dwarfs yet. According to ESA's Gaia mission, even the oldest white dwarfs in the Milky Way are still faintly glowing, radiating residual heat from their formation billions of years ago. But in the degenerate era, black dwarfs will be everywhere, countless billions of them drifting through the darkness, invisible and inert. Neutron stars are even stranger. These objects form when massive stars explode as supernovae, leaving behind cores compressed to unimaginable densities. A neutron star is about 20 kilometers across, but contains more mass than the Sun. According to NASA's NICER instrument aboard the International Space Station, a teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity is so strong that atoms are crushed, protons and electrons forced together to form neutrons. Some neutron stars are pulsars, spinning rapidly and emitting beams of radiation that sweep across space like cosmic lighthouses. The fastest pulsars rotate hundreds of times per second, their magnetic fields generating electromagnetic pulses detectable across vast distances. But even pulsars slow down over time. As they radiate energy, their rotation decelerates. According to observations by NASA's Fermi Gamma Ray Space Telescope, pulsars can remain active for millions or even billions of years, but eventually they spin down and go silent. In the degenerate era, neutron stars will still exist, but they'll be cold, dark, and silent, no longer spinning rapidly, no longer emitting pulses, just dense, inert spheres drifting through space. They'll last effectively forever, barring any collisions or other interactions. Neutron stars don't decay. They don't evaporate. They simply exist, unchanging, for incomprehensible stretches of time. But the degenerate era isn't completely static. Even though fusion has stopped, even though stars no longer burn, there are still occasional flashes of activity. Brown dwarfs, objects too small to ignite fusion, will occasionally collide with planets or other brown dwarfs, releasing brief bursts of heat and light. White dwarfs might accrete matter from passing gas clouds, temporarily reigniting fusion on their surfaces in events called novae. And there's another possibility, speculative but intriguing. According to some models of stellar evolution, white dwarfs made primarily of carbon and oxygen might eventually undergo crystallization. The carbon atoms, cooled to near absolute zero, could arrange themselves into a diamond-like lattice. These diamond stars would be the largest diamonds in the universe, each one containing the mass of a star compressed into a crystal the size of Earth. ESA's Euclid mission, mapping the large-scale structure of the universe, will help astronomers understand how matter is distributed across cosmic time. But even Euclid won't see the degenerate era. That future lies trillions of years ahead, far beyond the reach of any observation. We can only infer it from physics, from the laws governing how matter behaves, how objects cool, how the universe evolves. The galaxies themselves will change during this era. According to simulations by NASA's Jet Propulsion Laboratory, galaxies don't remain stable over trillions of years. Stars slowly drift apart due to gravitational interactions. Close encounters between stars, though rare, can fling some stars out of the galaxy entirely, sending them into intergalactic space as rogue stars. Over time, this process, called dynamical relaxation, causes galaxies to slowly evaporate, losing stars to the void. Meanwhile, the central black holes in galaxies continue to grow. As stars pass near the black hole, some get captured and devoured. According to NASA's Event Horizon Telescope, the supermassive black hole at the center of our Milky Way, Sagittarius A, contains about 4 million solar masses. Over trillions of years, it will grow larger as it consumes stars, gas, and even other black holes. But even black holes aren't permanent. In 1974, Stephen Hawking predicted that black holes slowly evaporate through a quantum process now called Hawking radiation. Black holes emit faint thermal radiation, losing mass over time. For a black hole the size of Sagittarius A*, the evaporation time is about 10 to the power of 87 years, a number so large it defies comprehension. But it's not infinite. Eventually, even black holes die. By the end of the degenerate era, around 10 to the power of 40 years from now, the universe will be a very different place. Galaxies will have dispersed, their stars scattered across expanding space. Most stars will have become black dwarfs or neutron stars, cold and dark. A few will have been consumed by black holes, and the black holes themselves will have grown, merging with each other, becoming the dominant objects in the universe. As cosmologist Brian Greene once said, "The universe is a story of transformation, from simplicity to complexity, and back to simplicity again." The degenerate era is part of that return to simplicity, a time when the intricate structures of stars and galaxies give way to simple, inert objects scattered across an ever-expanding void. Take a quiet breath. In 100 trillion years, the last star will have gone dark. The universe will be cold, black, filled with the corpses of stars. No sunlight will warm any planet. No starlight will illuminate any sky. Just darkness, broken occasionally by the faint glow of matter falling into black holes and the even fainter radiation from the black holes themselves. And as we contemplate this dark future, another question arises. If even dead stars eventually disperse, if galaxies evaporate and black holes grow, what happens in the even more distant future? That's where we turn next. Part 3, the black hole era. When only darkness remains. By the time we reach 10 to the power of 40 years, roughly a trillion years from now, the universe will have entered the black hole era. This is the period when black holes are the only significant objects left, when everything else, stars, planets, neutron stars, white dwarfs, has either fallen into black holes or dispersed into the void. It's an age of profound darkness, where the largest objects in the universe are also the darkest. Black holes are not empty space. According to Einstein's general theory of relativity, they're regions where space-time is curved so sharply that nothing, not even light, can escape once it crosses the event horizon. Inside, at the center, lies the singularity, a point of infinite density where the known laws of physics break down. But from the outside, a black hole is defined entirely by three properties: mass, spin, and electric charge. Everything else about the matter that formed it is lost, hidden behind the event horizon. According to NASA's Chandra X-ray Observatory and ESA's XMM Newton satellite, black holes come in several sizes. Stellar mass black holes, formed from collapsed stars, range from a few to a few dozen solar masses. Intermediate mass black holes, still somewhat mysterious, might exist in dense star clusters, and supermassive black holes, with millions or billions of solar masses, lurk at the centers of most galaxies. In the black hole era, these supermassive black holes will dominate. They'll have consumed most of the matter in their vicinity: stars, gas, even smaller black holes. According to simulations by NASA's Goddard Space Flight Center, black holes grow through accretion and mergers. When two black holes orbit each other, they emit gravitational waves, ripples in space-time that carry away energy. This causes the black holes to spiral closer together, eventually merging into a single, larger black hole. The LIGO and Virgo observatories have detected dozens of these mergers, events that occurred billions of years ago, but whose gravitational waves only reached us recently. Each merger creates a brief, violent disturbance in space-time, releasing more energy in a fraction of a second then all the stars in the observable universe emit in the same time. But after the merger, calm returns. The new black hole settles into a stable state, spinning gently, waiting for its next meal. But here's the profound mystery. Black holes don't last forever. In 1974, Stephen Hawking made a revolutionary discovery. Black holes emit radiation. Near the event horizon, quantum fluctuations create pairs of particles, one with positive energy and one with negative energy. Sometimes, the negative energy particle falls into the black hole, reducing its mass, while the positive energy particle escapes as radiation. This process, called Hawking radiation, causes black holes to slowly evaporate. For large black holes, the process is incredibly slow. According to calculations based on Hawking's equations, a black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole with a billion solar masses would take about 10 to the power of 100 years. These timescales are so vast, they make the current age of the universe, 13.8 billion years, seem like an eye blink. But here's the strange part. As a black hole evaporates, it gets hotter. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Larger black holes are colder, barely above absolute zero. But as they lose mass, they heat up. In the final moments, when a black hole has shrunk to microscopic size, it becomes incredibly hot, radiating away its remaining mass in a final burst of energy before vanishing completely. ESA's planned LISA mission, a space-based gravitational wave observatory, will detect mergers of supermassive black holes billions of light years away. These observations will help us understand how black holes grow and evolve. But LISA won't see the black hole era. That future lies so far ahead that it's beyond the reach of any conceivable observation. We can only infer it from physics, from the mathematics of general relativity, and quantum mechanics. In the black hole era, the universe will be almost completely dark. Black holes don't shine. They absorb light, bending it into their event horizons, allowing nothing to escape. The only light will be the faint Hawking radiation, imperceptible at first, slowly brightening over incomprehensible timescales as the black holes shrink. And there's another source of faint light: proton decay. According to some theories in particle physics, protons, the particles that make up atomic nuclei, are not stable. They might decay into lighter particles over extremely long timescales, around 10 to the power of 36 years or longer. If protons decay, then all matter, everything made of atoms, will eventually disintegrate. White dwarfs, neutron stars, planets, asteroids, all will slowly dissolve into radiation and lighter particles. NASA's Super Kamiokande detector in Japan has searched for proton decay, but found no evidence of it. If protons do decay, the process is so slow that we haven't detected it yet. But over the timescales of the black hole era, even rare events become inevitable. If protons decay, then by 10 to the power of 40 years, most matter will have vanished, leaving behind only radiation and black holes. The universe at this stage will be almost unrecognizable. No stars, no planets, no structures, just black holes, slowly evaporating in an ever-expanding void. The expansion itself, driven by dark energy, continues relentlessly. According to ESA's Planck satellite, dark energy makes up about 68% of the universe's total energy, and it pushes space apart at an accelerating rate. As the universe expands, the density of matter decreases, and the average temperature drops. By the black hole era, the temperature of empty space, defined by the cosmic microwave background, will have cooled to almost absolute zero. The photons that fill the universe, stretched by billions of years of expansion, will have wavelengths longer than galaxies. Their energy will be negligible, their presence detectable only by the most sensitive instruments, if such instruments could even exist. And in this cold, dark, empty universe, black holes will be the last complex structures. They'll drift through the void, alone, slowly radiating away their mass. According to physicist Freeman Dyson, this era represents the final stage of gravitational dominance. After the black holes evaporate, there will be nothing left capable of exerting significant gravitational influence. The universe will enter its final phase. Take a long, slow breath. In 10 to the power of 100 years, the last supermassive black hole will evaporate. It will shrink slowly at first, then faster, heating up as it loses mass. In its final moments, it will shine briefly, a flash of radiation marking the end of the last structure, the last object capable of complexity. And then it will vanish, leaving behind only photons and particles dispersed across an infinite, expanding void. And as we watch the last black hole fade, a final question emerges. What happens after? When even black holes are gone, when nothing remains but radiation and empty space, what does the universe become? That's where our journey ends. Part 4. The Dark Era, Heat Death and the End of Everything. After the last black hole evaporates, sometime around 10 to the power of 100 years from now, the universe enters what cosmologists call the Dark Era, or more formally, the photon epoch. This is the final stage, the state toward which the universe has been drifting since the moment of the Big Bang. It's the end prophesied by the second law of thermodynamics, the principle that entropy, the measure of disorder, always increases in a closed system. At this stage, the universe will consist almost entirely of photons, the particles of light, and leptons, elementary particles like electrons, neutrinos, and their antiparticles. These particles will be spread so thinly across space that the average density will be close to zero. According to NASA's WMAP mission and ESA's Planck satellite, the universe is already quite empty, with an average density of about 5 atoms per cubic meter. But in the dark era, it will be far emptier. Particles will be separated by distances larger than galaxies are today. The temperature will be astonishingly low. The cosmic microwave background, now at 2.7 degrees above absolute zero, will have cooled to essentially zero. According to the laws of thermodynamics, this means that all temperature differences will have vanished. Heat, which flows from hot to cold, will have no gradient to follow. Energy will be evenly distributed, incapable of doing work, incapable of driving any process. This is what physicists call heat death, though it's more accurately a cold death. The universe won't be destroyed. It will simply reach a state of maximum entropy, where nothing can change, where no energy is available to power any process, where time, in any meaningful sense, stops having significance. Events might still occur, particles might still move, but without structure, without complexity, without the ability to organize or create, the universe will be effectively dead. Hermann von Helmholtz first proposed this idea in the 19th century, and it troubled philosophers and scientists alike. The thought that the universe, despite all its beauty and complexity, is destined to fade into cold, lifeless equilibrium seemed nihilistic, almost unbearable. But the mathematics is clear. The second law of thermodynamics is inviolable. Entropy increases. Order becomes disorder. Complexity simplifies. As physicist Brian Greene explains, the arrow of time, the reason we remember the past but not the future, the reason eggs break but don't spontaneously reassemble, all stem from the universe's journey from low entropy to high entropy. The Big Bang was a state of extremely low entropy, highly ordered, with energy concentrated in a small hot region. Since then, the universe has been spreading out, cooling down, increasing its entropy. The dark era is the endpoint, the state of maximum entropy from which no further change is possible. But is it truly the end? Some physicists have proposed that even in the dark era, interesting things might occasionally happen. According to quantum mechanics, the vacuum is never truly empty. Virtual particles constantly pop into existence and annihilate each other, borrowing energy from the vacuum for infinitesimally short times. These quantum fluctuations are usually too small to notice, but over the timescales of the dark era, they might lead to rare but significant events. One possibility is Boltzmann brains, hypothetical entities that spontaneously form from random fluctuations in the vacuum. The idea, proposed by physicists Sean Carroll and others, is that in an infinite universe with infinite time, even incredibly unlikely events must eventually occur. A random fluctuation might briefly create a conscious observer, a brain floating in space with memories and thoughts, before it dissipates back into randomness. This scenario, while mathematically possible, raises profound philosophical questions. If most observers in the universe are Boltzmann brains, fleeting hallucinations in an otherwise dead cosmos, how can we trust our own perceptions? Are we real? Or are we just a momentary fluctuation? Most physicists, including Carroll himself, consider Boltzmann brains more a problem to be avoided than a serious prediction. Their existence would undermine the foundations of science. Another possibility is quantum tunneling to a new vacuum state. According to quantum field theory, the vacuum of space might not be in its lowest energy state. If a lower energy state exists, the vacuum could spontaneously tunnel to it, releasing enormous energy and potentially creating a new universe with different physical laws. This process, if it occurs, would be incredibly slow, taking far longer than even the timescales of the Dark Era. But it offers a glimmer of possibility, a way for the universe to reinvent itself even after apparent death. Physicist Roger Penrose has proposed a more radical idea: conformal cyclic cosmology. In this model, the universe doesn't end with heat death. Instead, when all matter has decayed and only massless particles remain, the universe forgets its size. Without massive particles to define a scale, space-time becomes conformally invariant, and the smooth, empty end of one universe becomes the smooth, empty beginning of the next. The Big Bang of a new universe emerges from the cold death of the old one, creating an endless cycle of cosmic rebirth. These ideas are speculative. We have no direct evidence for vacuum tunneling, Boltzmann brains, or cyclic cosmology. They're attempts to find meaning or possibility in what appears to be an ending, to imagine that even in the dark era, the universe might surprise us. But the most straightforward interpretation of our current physics is that the dark era is final. The universe will reach a state of cold, dark, empty equilibrium and remain there, unchanging, for eternity. NASA's upcoming missions, including the Nancy Grace Roman Space Telescope and next-generation particle physics experiments, will help us understand dark energy, the force driving cosmic expansion. If dark energy changes over time, it could alter the timeline. The universe might expand forever, collapse in a big crunch, or even tear itself apart in a big rip. Each scenario leads to a different ending. But current observations suggest that dark energy is constant, leading inexorably to cold death. ESA's Euclid mission, mapping billions of galaxies, will provide more precise measurements of the universe's expansion history. But even with perfect data, we can't observe the far future directly. We can only extrapolate, using the laws of physics to project forward, to imagine what the universe will become when all stars have died, all black holes have evaporated, and all energy has dissipated into the void. As Carl Sagan once said, "The cosmos is all that is, or ever was, or ever will be." But the cosmos changes, it evolves, it ages, and eventually, according to our best understanding, it reaches a state where nothing more can happen, where the story ends not with a bang, but with an infinite, silent whisper. Take one last, slow breath. In 10 to the power of 100 years, maybe 10 to the power of 1,000 years, the universe will be dark, cold and essentially empty. Photons will drift through space, their wavelengths stretched to absurd lengths. Particles will be separated by distances so vast that they might as well be in separate universes. And time, which once brought change, novelty, and complexity, will bring only more of the same: emptiness, silence, stillness. This is the cold death of the universe, the timeline we cannot escape, the ending written into the laws of physics themselves. It's not violent, it's not dramatic, it's just a fading, a dimming, a long, slow slide into equilibrium. And yet, within that ending, there's a strange kind of peace, a reminder that even the universe, vast and ancient as it is not eternal. Everything ends, even the cosmos itself. Part 5. What it means to exist in a dying universe. So here we are, you and I, living in a universe that is slowly dying, that has been dying since the moment it was born. Every star that shines is burning fuel it can never replace. Every galaxy that spins is gradually losing its structure to entropy. Every moment that passes brings the cosmos one infinitesimal step closer to cold, dark equilibrium. This might sound depressing, almost nihilistic. If everything ends, if all stars die, if the universe itself fades into nothingness, what's the point of anything? But there's another way to see it. The fact that the universe is dying doesn't diminish the beauty of the time we have. In fact, it amplifies it. We live in the stelliferous era, the brief cosmic moment when stars are common, when galaxies glow with light, when complexity and life are possible. According to NASA's Hubble Space Telescope and the James Webb Space Telescope, we're living in a universe filled with wonders: spiral galaxies, nebulae glowing with the light of newborn stars, planets orbiting distant suns, black holes spinning at the edge of comprehension. This age will pass. In 1 trillion years, it will be over. But right now, it's happening, and we're here to witness it. Carl Sagan once said, "We are a way for the cosmos to know itself." That knowing is precious, not despite the universe's mortality, but because of it. We are temporary patterns of matter and energy, brief sparks of consciousness in a vast, ancient cosmos. But during our moment, however brief, we can ask questions, make discoveries, feel wonder, experience love, and understand, however incompletely, the nature of the reality we inhabit. The timeline of cosmic death is incomprehensibly long. The stelliferous era lasts about 100 trillion years. The degenerate era might last 10 to the power of 40 years. The black hole era could extend to 10 to the power of 100 years or longer. These numbers are so vast that human minds can't truly grasp them. But they're not infinite. The universe has an age, a history, a future, and eventually, an ending. Time itself might be finite in a meaningful sense. This realization changes how we think about existence. Physicist Freeman Dyson once explored whether intelligence could survive in the far future, as the universe cooled and resources dwindled. He concluded that by slowing down, by thinking more slowly as energy became scarce, a sufficiently advanced civilization might survive indefinitely, experiencing an infinite number of thoughts even as the universe approached cold death. This idea, while speculative, suggests that even in a dying universe, there might be ways to persist, to adapt, to find meaning. But most physicists are more pessimistic. As the universe expands and cools, as structures disperse and black holes evaporate, the resources needed to support complexity, let alone life or intelligence, disappear. According to the second law of thermodynamics, the universe is moving toward a state where work cannot be done, where energy cannot be organized, where even the simplest processes become impossible. In this view, consciousness, life, and intelligence are temporary phenomena, possible only in the relatively warm, dense, structured universe of the early eras. Once the dark era arrives, these phenomena will cease. never to return. We are, in a sense, living in a privileged time, the brief window when the universe is warm enough, structured enough, and young enough to support beings capable of asking questions about their own existence. This perspective has echoes in philosophy and literature. The ancient Greeks spoke of entropy, though they didn't use that word. They understood that things break down, that order gives way to chaos, that even empires and civilizations eventually crumble. The second law of thermodynamics gives this intuition a precise mathematical form. Entropy always increases. The universe always moves from order to disorder. But within that overall trend, local reversals are possible. According to ESA's Planck satellite and NASA's observations of the cosmic microwave background, the early universe was remarkably smooth and uniform, with only tiny fluctuations in density. Over time, gravity amplified those fluctuations, pulling matter together into stars, galaxies, and planets. Locally, structures formed, order increased, entropy decreased, even as the universe as a whole moved toward greater disorder. Life is one of those local reversals. On Earth over billions of years, simple molecules organized themselves into cells, then into complex organisms, then into ecosystems. Entropy increased in the environment. Energy was dissipated as heat. But locally, within living systems, complexity grew. This is allowed by thermodynamics because Earth is not a closed system. Energy flows in from the sun, driving the processes that sustain life. But the sun itself is temporary. In 5 billion years, it will exhaust its hydrogen and begin its death throes. Earth will be consumed or rendered uninhabitable. Life, at least life as we know it, will end here. But perhaps by then, if we survive, we'll have spread to other stars, other planets, continuing the story across the galaxy. Yet, even that is temporary. The galaxy itself will eventually run out of stars. The stelliferous era will end. And life, unless it can adapt to a cold, dark universe devoid of stars, will end with it. As cosmologist Lawrence Krauss writes in A Universe from Nothing, the universe is heading toward a state where life cannot exist, where even the building blocks of life have dispersed beyond any possibility of reuniting. This is the timeline we cannot escape. Not because of any failure of imagination or technology, but because of the fundamental laws that govern reality. Entropy increases, stars burn out, black holes evaporate, the universe cools. These processes are not optional. They are woven into the structure of space-time itself. And yet, knowing this doesn't have to lead to despair. Physicist Sean Carroll argues that the arrow of time, the increase of entropy, is what gives life meaning. Without the arrow of time, there would be no causality, no memory, no life, he writes. The very fact that we exist, that we can think and feel and wonder, depends on the universe being far from equilibrium, on the availability of free energy, on the temporary nature of order. In this view, our existence is made meaningful by its rarity and impermanence. We are not eternal, neither is the universe. But during the time we have, we can experience beauty, create art, love one another, and seek understanding. The ending doesn't negate the journey. It gives it weight, urgency, and significance. The James Webb Space Telescope, peering back to the earliest moments of cosmic history, shows us galaxies forming, stars igniting, the universe coming alive. ESA's Euclid mission, mapping the large-scale structure of the cosmos, reveals the intricate web of galaxies, the patterns of matter and energy that define our era. These missions remind us that we live in a time of incredible richness, a cosmic moment filled with light, structure, and possibility. That moment will pass. The timeline is set. The ending is written in the equations of thermodynamics and general relativity. But the fact that it will end doesn't diminish what is. Right now, The universe is alive. Stars are burning. Planets are orbiting. Life is evolving. And somewhere, on a small planet orbiting an ordinary star, consciousness has emerged, capable of looking up at the night sky and asking, how does it all end? The answer is simple and profound. It ends in cold and darkness, in the dispersal of all structure, in the slow fade to equilibrium. But before that ending, there is this. There is now. There is light and warmth and life, and that perhaps is enough. Conclusion? The long goodbye. So we've traveled to the end, followed the timeline from the present day to the unimaginable future, from the stelliferous era to the dark era, from a universe filled with light to one drowned in cold and emptiness. It's a journey measured not in millions or billions, but in trillions, quadrillions, and numbers so large they lose meaning. And at the end of that journey, there is no grand finale, no cosmic explosion, just a slow fading, a long goodbye. The cold death of the universe is not a failure, it's a fulfillment, the natural end of a process that began with the Big Bang. The universe was born in a state of low entropy, highly ordered, and it has been evolving ever since, spreading out, cooling down, moving inexorably toward equilibrium. Stars are not eternal. Galaxies are not permanent. Even black holes, the most enduring structures in the cosmos, eventually evaporate into radiation. Everything ends, even the universe itself. But that ending lies so far in the future that it's almost abstract. Right now, you are living in the universe's golden age, the stelliferous era, when stars are abundant, galaxies are bright, and life is possible. This era will last for trillions of years, longer than human minds can truly comprehend. For us, for our children, for countless generations to come, the universe will remain a place of wonder, beauty, and mystery. The timeline we cannot escape is not a reason for despair. It's a reminder that existence is precious precisely because it is temporary. Every star that shines is burning fuel it cannot replace. Every moment of life is a victory against entropy. Every thought, every feeling, every connection we make is an act of defiance against the universe's drift toward disorder. As you drift off tonight, remember this. You are made of stardust, atoms forged in the cores of dying stars billions of years ago. Those atoms have come together, briefly, to form you, a pattern of matter and energy capable of thought, of wonder, of love. That pattern will not last forever. Nothing does. But right now, in this moment, you exist. And that existence, however temporary, is part of the universe's story, part of the long arc from the Big Bang to cold death and beyond. The universe is dying. It has been since the moment it was born. But it's not dead yet. And neither are you. So take comfort in the light while it lasts, in the warmth of stars, in the beauty of galaxies, in the complexity of life. The ending is coming, but it's not here yet. And until it arrives, the cosmos is still singing, still shining, still turning. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply. Until next time, may you find comfort in the temporary nature of all things. May the eventual cold death of the universe remind you to cherish the warmth while it lasts. And may you rest easy, knowing that here, now, in this brief cosmic moment, you are alive, aware, and part of something vast, ancient, and endlessly beautiful. The universe is dying, but tonight it's still here, and so are you.